high contrast adaptive optics imaging, latest results in direct exoplanet imaging. And we're starting with an invited review by Beth from Heidelberg, detecting and characterizing exoplanet via direct imaging, past, present, and future.
All right. I think this is not on now. No? All right. The green light is on, but it's not picking up. We have to have the, oh, there it is, okay. Okay, well, we keep it, no, higher up. All right, how about now? Cool, yay. Well, I'm glad that was only the requisite 30 seconds of fiddling around with the microphone. I'm very excited to be here today to talk to you and to open the conference by discussing the rapidly growing field of direct imaging of exoplanets. Direct imaging has a huge potential for really revolutionizing our understanding of extrasolar giant planets and the systems that they inhabit, especially now that we have a small but significant population of directly imaged planets and close to planetary things. So these objects here, they have estimated masses of 20 Jupiter masses or less, and they are all confirmed companions to stars or brown dwarfs. And now that we do have on order 10 to 20 such detections, we can start really beginning to answer some fundamental questions about exoplanets. So I like to group these fundamental questions into a couple of main themes. The first of these are physical properties. And this is the real value of methods of planet detection, like direct imaging, that yield photons directly from the planet itself. So we'd like to know the masses of planets. We'd like to understand their compositions, their temperatures, and we have photons from planets. This is much easier to do. And in this talk, I'm going to focus especially on what we can say about atmospheres of young giant planets from direct imaging. Theme number 2 is architecture. Where do planets tend to live in their planetary system? And with many large-scale direct imaging planet surveys completed or soon to be completed, we can start putting some very strong constraints on the distribution of wide giant planets. Direct imaging is rather technically difficult, so I wanted to just devote a couple of slides to how we do this in the first place. There are two main concerns in terms of directly imaging exoplanets. The first is rather obvious. There's a huge contrast difference between the star and the planet. So for something like Jupiter, we're talking about a factor of 10 to the 9th, which is really quite daunting. That's why, to date, this field has focused largely at observing young objects in the near infrared, because they're predicted to be somewhat brighter at young ages, and you expect to find contrast ratios between the star and the planet from 10 to the 4th to 10 to the 7th, depending on what set of models you look at. So to get these contrasts, you have two choices. You can either get rid of the atmosphere by working in space, or you can use adaptive optics from the ground to basically move the light out of the seeing limited halo into the core of your PSF and reveal faint companions. Once you get good enough corrections, you can then use a chronograph to get even better contrasts. There are a very wide variety of different chronograph architectures. That could be a whole talk, or in fact, a whole conference of its own. This is one example. This is a LEO chronograph. And like most chronographs, it consists of a simple part and a complicated part. So the simple part here is your Colting spot, where you just block out the star. Pretty straightforward. And then here, in your pupil plane, you use a LEO stop or another architecture to clean up the pupil itself and remove up to 99% of the scattered starlight. But even so, you haven't completely corrected everything, and you'll likely still suffer from issue number 2, which is speckle noise. This is 2 minutes of data from the NACO adaptive optics camera at the VLT. I've smoothed this and subtracted it from itself to basically remove the starlight and bring out this speckle pattern. All these little speckles do a really good job of simulating planets. And the issue here is that they're not static. They move around. In ground-based data, they move around on hour timescales. In space-based data, they're still there, and they move around on, say, day timescales. So you can't just integrate longer and get a higher signal-to-noise with this data. You need to use some sort of instrumental method to get past this speckle noise floor. And one that's become industry standard is angular differential imaging, where you use rotation on the sky to decorrelate a real object from a speckle. So this is from the near-infrared chronographic imager. You can choose to look at whichever of the two channels you want to. And we've turned off the rotator, and we just let the field of view rotate on the sky with a parallactic angle. And when you do that, sometimes your movie doesn't work. All right. So if it was working, what you would see is that the star and the speckles just wobble around. They don't care what the parallactic angle is, whereas your real object moves with the parallactic angle on the sky. And obviously, for a wide object like this, it doesn't make a big difference. But if this is closer in, it can be the difference between detecting this object or not. So you can just derotate and stack your images, and that already reduces your speckle noise. But what's much more powerful is if you use different techniques to build an ideal PSF from all the different images in your stack. And in fact, techniques like this were pivotal for this first infrared exoplanet image. And I want to point out there's a number of posters and talks that discuss basically development of different sorts of algorithms and techniques to do this. So starting about 10 years ago and ending 5 or 6 years ago, there was a first generation of surveys that combined some, but not all of these techniques I just talked about. Mostly they combined 8-meter class telescopes with adaptive optics and techniques such as ADI, but didn't have chronographs. But they still put some very interesting limits on the distribution of wide giant planets. So this is statistical results from Nielsen and Close 2010, combining 3 different surveys and over 118 stars from all 3 surveys. And what you're looking at here, this is the result of a Monte Carlo simulation for each semi-major axis mass pairing. Nielsen and Close simulated 10 to the 4th possible planets. Other orbital parameters were just taken randomly. Compare that to the contrast curves achieved for each of the different survey stars and determined what fraction of those simulated planets could be detected at each particular point. And then use that to put upper limits on the possible planet fraction, given that this particular survey had a null result. So what you can see here is at the 95% confidence level, we pretty much don't see a lot of planets. Less than 20% of stars should have 4 Jupiter mass planets at wide separations from 50 to a few hundred AU. So we already know that this area is fairly bereft of planets, but with newer imaging efforts, we can actually push a bit inward and deeper. So I'm going to talk a little about some of the ongoing and recently completed direct imaging efforts. These combine all 4 of the advanced techniques I've been telling you about. So 8-meter class telescope, plus AO, plus a chronograph, plus advanced speckle suppression techniques. And these are largely the large-scale surveys. There are some smaller-scale surveys that I'll highlight in some further slides and will be discussed by other people later in this conference. But in terms of surveys with more than 100 stars in them, there's the Nikki Science Campaign, using a near-infrared chronographic imager at Gemini South. This is a 230-star survey that was completed in 2012A. And Mike Liu and Eric Nielsen will be presenting posters on this later in this program. There's the NACO Large Program, which is a survey using the NACO camera at VLT. And Artur Vigan is going to talk about that later this session. IDPS is another large-scale survey combining Keck and Gemini. And Raphael Galichet will talk about that later today as well. SEEDS is a 5-year program at Subaru using the Haichao camera. It's about halfway through, and Tamura-san will give an overview. Tim Brandt has a poster on that as well. PALMS is planets around low-mass stars using Haichao at Subaru. Brendan Bowler will talk about that later. And LEACH is, in fact, the newest of these surveys. This is using Elmer Cam at the very novel LBT-AO system. And it actually began in February. And unlike the rest of these surveys, LEACH is working in the mid-infrared at extremely high strels. So at this point, I just also want to give a little plug for all these surveys, or what you can do with survey data, we have a database called DIVA within the SPHERE consortium that we're trying to, basically, if you have no results from these surveys and you'd like to help compile them so that we don't all try to look at the same star that doesn't have planets, we'd really appreciate your help in putting that together. And Artur Vigan and Raphael Galichet will talk about that a little more. So I wanted to highlight a couple of subsamples of stars that various of these surveys are targeting. And I'm going to start with A stars. So 10 years ago, most direct imaging surveys did not tend to target A stars. And the reason is, on the surface, they looked like they were a bad bet. They're very bright, so even with very good contrast, you might not be able to detect much that was planetary. Since then, there's been 2 lines of evidence that suggest that they are quite interesting targets. The first is from radial velocity studies of planet hosts at a variety of stellar masses. And what has been found for closer-in planets, this is, within 3 AU or so, is that A stars do tend to preferentially host more giant planets than lower mass stars. And the second line of evidence is simply that there's a number of high-profile detections of exoplanets around A stars. So based on this, a number of surveys have focused strongly on A star populations. This is results from NICI, from a sub-survey from the NICI campaign of 70 A and B stars. And while there's been a number of high-profile detections, it does look that A stars still relatively rarely host wide separation planets. So at the 3 or 4 Jupiter mass level, it seems to be about similar results as from the earlier planet surveys that focused more on young solar analogs. So at the absolute opposite side of the mass spectrum, M stars have also generally been not as well covered by direct imaging surveys because radial velocity results suggest that they don't tend to host Jupiter mass or smaller planets or larger planets that frequently. But there are a number of surveys targeting M stars that are getting some very interesting results. So this is the detection of a 12 to 14 Jupiter mass companion around binary M star. So perhaps M stars are not quite as much of a planet desert as we think at wide separations. Additional interesting subsamples that have been getting a lot of attention lately include debris disk stars. The existence of a debris disk is a pointer that you may have planets in the system. Well, you do. And so they seem like sensible places to look. Moving group stars are another interesting subsample. And these stars, of the young stars we tend to survey, have the best determined ages and quite well determined distances. So they're very valuable in terms of if you detect something, if it's around a moving group star, you're going to have a much better chance of really pinning down its properties if you're plugging into models and you really need to know the distance and the age well. Another interesting subset are RV trend stars. So these are generally older stars that show trends in radial velocity data. And these haven't shown a clear periodicity, so it implies that there is something around these objects, but at wider separations. So there are a number of surveys looking for trying to directly image whatever is causing this RV trend. So these surveys are generally reaching quite good contrast. This is just an example set of contrasts with NICI. This is a subsample of moving group stars, actually in the AB Door moving group. And these are super, super typical. I'm showing these mostly because they're super, super typical of what has been achieved in the NICI campaign. So at 1 arc second, the median contrast achieved is about 10 to the 5th between the star and the planet. And this is sufficient that we're quite sensitive to 3 Jupiter mass and greater planets at separations of 20 AU or more across the entire young sample. So again, this is typical with NICI. Other surveys are also getting quite similar contrasts as this. And with these sorts of contrasts and ability to really either find planets that are there or if we don't see them, put really strong constraints on their frequency, we're beginning to really be able to answer some of these fundamental questions about exoplanets. So I want to start first by discussing physical properties, especially what we're learning about atmospheres of young planets from direct imaging. These aren't actually survey results as much as follow-up of things that were either discovered with surveys or serendipitously. And this is kind of the highlight reel. There's a lot of other very interesting results that I don't have time to mention in detail today. So as I noted, we have this small but growing group of directly imaged planetary or nearly planetary companions. In fact, it grew a little more even today. So this appeared on AstroPH today. And this is a new 4 to 5 Jupiter mass companion. We also have an interesting set of benchmark brown dwarf companions that have been discovered as part of these surveys. Interestingly enough, most of these objects, 5 out of 6 of these, are 20 to 30 Jupiter mass brown dwarfs, 30 to 40 Jupiter mass brown dwarfs sitting right within the so-called brown dwarf desert. This one is a somewhat higher mass object. This is a 50 to 60 Jupiter mass companion, but it's very close in, so it's likely to yield a good orbit in the short term. And this group of objects has grown recently too. This is a result from marginally resolved object from the Nikki campaign, and check out Eric Nielsen's poster for more details on this one. But for all these detections, since we have direct photons from the planets or the brown dwarfs, we can start saying a lot about their properties just from colors. So typical HR diagram here, and there's a number of different groups of objects plotted. So these here are T-dwarfs. And they are characterized by clear atmospheres, methane absorptions, and comparatively blue infrared colors. 10 years ago, if you asked someone in the field of direct imaging, what do you expect a young planet to look like? They probably would say, like a T-dwarf. They have the same effective temperature, and so they should have the same properties. But while they share effective temperatures with T-dwarfs, young planets do not have the same surface gravity. They're actually at much lower surface gravity. And so it's not that surprising that we actually find that they don't sit on this T-dwarf sequence, but are in fact quite a bit redder. So this is 3 of the HR8799 planets in 2 mass 1207b. And you can see considerably redder than these T-dwarfs. In fact, they seem to really follow pretty well this L-dwarf sequence here. L-dwarfs are a bit hotter and are characterized by red colors due to dusty clouds in their atmospheres. So this implies strongly that these T-dwarfs, in fact, also, not T-dwarfs, young exoplanets, in fact, share these thick, dusty clouds. And you can see in terms of models, basically these are model contours where here's the cloud-free models, and as you move towards the right, you just are adding more and more cloud. So immediately we know that these red colors are likely due to clouds. We do even better when we can do direct spectroscopy and not just imaging in a couple of bands. So this is a recent result from Project 1640 at Palomar. And these were simultaneous spectra taken of all 4 HR8799 planets at once. These are very low resolution, R of about 35. But what's interesting immediately about this is that while these 4 planets all share fairly similar masses, they all formed in the same disk from the same material and have the same age, these spectra look quite different. B and C are best fit as L-dwarfs. D is more T-dwarfy, and E, their best fit for this was Saturn. It's obviously somewhat limited by resolution, but it's an interesting result that there's so much spectral diversity, even in planets that form in the same system. You can do even better with somewhat higher resolution spectra. So here are spectral results for HR8799b, the widest of the HR8799 planets. And what's immediately notable is the methane absorption feature that everyone thought the young planets were going to have 10 years ago don't appear to be there, so no methane absorption really in the K band or in the H, or if so, only very weak, but clear evidence of a possible CO absorption line. So given that these probably do have effective temperatures, should have effective temperatures less than L-dwarfs, it's likely a surface gravity effect that is causing CO to predominate here over CH4. In other words, there's some sort of non-equilibrium chemistry that's causing this particular sort of composition, or at least what we measure. So you do even better with higher resolution spectra. And Quinn has a poster on this in this conference too. This is an R of 4,000 spectra of HR8799c, a closer in planet. As you can see, it has a very clear CO absorption feature. And this team fit spectral models here to try to look at the composition of this object, in particular to look at the C to O ratio and the relative abundance of C and carbon and oxygen. And what they found is the C to O ratio is a bit higher than solar, whereas C and O respectively are a bit depressed relative to solar. And this they interpret as evidence that this is a core accretion object. Assuming that the disk of HR8799 has solar composition, a disk instability planet should form an object with the same composition as the disk. So the fact that this composition is likely different is possible evidence that this is a core accretion planet. So another exciting possibility with direct imaging is eventually getting orbits for some of these objects as well. So for many of the wider separated companions, it's not really that realistic. We don't really have 1,000 years to wait around to follow the orbit at something at 50 AU. But for something like beta pic B at 8 to 10 AU, it already has enough of a time baseline that there are pretty good orbital estimations already. So this is results from Chavan et al. 2011, monitoring from 2003 up through 2011. And they've already put some interesting constraints on the most probable semi-major axis. And eccentricity for this object should be below 0.2 as well. All right, so now I've talked some about physical properties of exoplanets as determined by direct imaging. I'd like to move on to discuss architecture and what you can tell when you have a large-scale survey with very deep contrasts. I'm going to present today results from the full Nikki campaign sample. There are other surveys that have similarly large samples and are getting similar results, but this is finished and to date is the deepest survey published. So here are the upper limits on frequency for the Nikki campaign, assuming hot start models. This is a 270-star sample. 227 of these were observed with Nikki, 50 are from the literature. And again, this is the same sort of Monte Carlo simulation, where at each semi-major axis and mass point, simulated planets are then compared against the contrast curves for each star in the survey, and upper limits are set based on this. These are just radial velocity detections for comparison. And this does push in the results from previous surveys quite a bit. So inside the inner contour, fewer than 5% of stars can have a gas giant planet, i.e. something with mass of greater than 4 Jupiter masses at semi-major axes of 18 to 530 AU. So the astute listener might say, well, that's just hot start models. That's just one subset of models that assumes a certain evolutionary beginning to the planet. And I would say, yep, that's right. You have to consider the evolutionary history of the planet when making these sorts of statements, since these models play a huge role in converting contrast to what we can actually detect. So there's two flavors, and now there's in-between flavors too, of exoplanet evolutionary models. There's these hot start models, which are more or less equivalent to the case of a planet that formed via gravitational instability, where you just start with something that starts out at a very high entropy and then collapses. And they predict quite high luminosity for young planets that just trail off with age. If you want to look at models that have more realistic initial conditions for core accretion, then you have these cold start models, where you're accreting onto a rocky core. And they predict much lower luminosities at young ages, since you're not starting in as big and puffy of a state. And these, if we assume for now that hot start means essentially gravitational instability and cold start means essentially core accretion, we can then use this to try to constrain how well we understand both the populations of these planets. So where do we expect core accretion versus gravitational instability planets to live? This is more of a schematic. I'm not referring back to any particular set of models, but this is meant to be instructive more than anything else. Core accretion planets, if we're seeing them where they formed in situ and they haven't migrated around too much, we really only expect to find them within 10 AU or so. Whereas gravitational instability planets can form somewhat further out in the disk. And if you see something very far out, this implies that it was probably scattered out there. So what constraints can we put on gravitational instability planets from these NICI results combined with hot start models? Here are the same contours I showed previously. And what we can see is for the semi-major axis range where we expect to find gravitational instability planets, it looks pretty dry. We have a pretty robust result in terms of planet frequency. We get a pretty robust result also if we look at cold start models. It's less robust, obviously, because they're less luminous at the young ages that we look at these stars at. But we also still rule out a fair chunk of parameter spaces, although it is somewhat different from the regime where we actually expect to find core accretion planets. So planet frequency result does depend on its evolutionary history, but in both cases, we're putting strong constraints on the distribution of exoplanets. So for hot start models, we expect less than 10% of stars to have gas giant planets at semi-major axes of 10 to 810 AU. And for cold start models, we expect 10% or less of stars to have such planets at somewhat wider initial separations of 20 to 630 AU. So the summary of this, the takeaway from these results, is that hot start gas giant planets appear to be quite rare at semi-major axes of greater than 10 AU. This implies that analogs to HR8799b, and so the wider HR8799 planets, are quite rare. But there could be a lot of beta-pic analogs out there that we haven't detected yet. And if we assume that hot star corresponds to gravitational instability, which is indeed an assumption, then gravitational instability planets must be relatively rare. And we don't find a whole lot wider out too, so this implies that planet-planet scattering is relatively rare as well. So I'd like to close the talk by talking just a little, or really introducing some of the very exciting future directions in the next few years. There are a number of very exciting upcoming instruments, either just now on the sky or due to be commissioned soon. I'm just going to highlight 4. There are some additional ones as well. Check out posters on these. So there's SPHERE at the VLT, which is a dedicated planet finder imager for the VLT. GPI at Gemini, very similar instrument. These are both going to be very powerful instruments. They'll be coming on the sky soon. Project 1640 at Palomar is already on the sky and has yielded this simultaneous spectra for all 4 HR8799 planets. And SKEXAO is a high contrast coronagraph for Subaru. And these instruments and the surveys that will be conducted with them should yield quite a bit more planet detection. So for the near-Earth survey with SPHERE, which is a guaranteed time survey of 400 stars that will start with SPHERE probably in the next year or so. We've been doing Monte Carlo simulations of what we expect the planet yield to be for the entire survey, and best predictions with a range of different evolutionary models, different samples, and the best estimate of the contrast curve is that we would expect to detect 10 to 80 more planets as part of the near-Earth survey. So this will really help expand this small but growing population of objects. In the farther future, 10 years from now, ideally, we will have 3 extremely large telescopes from the ground and JWST from space. And I want to conclude with what I think is a really exciting prospect, which is the possibility of directly imaging an exo-Earth around one of the very closest M stars using an extremely large telescope and an extreme AO coronagraph. So this is results from Crossfield 2013, which is a simulation paper comparing predicted contrasts for an extremely large telescope plus an extreme coronagraph with the results in terms of low mass planet properties from Kepler. So the result is, the expectation is that we might detect up to 10 planets around the very nearest M stars with radii less than, say, 10 Earth radii and temperatures less than 500 Kelvin. And there is the possibility of also detecting an Earth analog, directly imaging it with an extremely large telescope. All right, so I think I'm about ready to conclude. The two takeaway points from this is on the heading of physical properties. Direct imaging has shown us that young exoplanets to date seem to have red colors consistent with dusty clouds in their atmospheres, as well as non-equilibrium chemistry. And in terms of architecture, the very good contrast being achieved by the current generation of surveys suggests that hot start gas giant planets are indeed quite rare at semi-major axes of 10 AU or greater. All right, cool. Thank you very much, and I'm happy to take some questions now.
Thank you very much, Debbie, Beth, for a very good talk.
Who's Debbie?
Questions? Here?
Oh yes, so one question, Beth. For the M-Dwarf survey, how many stars would they have to survey with the ELT to find 8 to 10 Earths?
No, there's just not that many that are good candidates. So they're basically looking at the ones within, say, 8 parsecs. So I would imagine, I mean, the 10 number is really, really the upper limit. It's more likely maybe 2 or 3 among a sample of maybe 20 stars.
Oh, thank you.
Here?
There you go. Here's your mic.
I had a boundary.
Can you take the microphone, please?
You had a boundary of 10 AU for core accretion, and above that, your hot start collapse model. You don't seem to be taking into account the mass of the star when you say that.
Yeah, and that's why I say that it's very much schematic. So most of the stars in the Niki sample tend to be more towards young solar analogs.
Yeah.
But it is, you know, if I was to show that just for the A-star sample, it should, I didn't mean to go back that way. It should be shifted. So,
because you're the beautiful example of 8799 is an A star, isn't it?
yeah, and so yeah, you would expect to have a more massive disk, and you should expect to see coefficients.
Yes, so we
that.
can't really say, probably.
Yeah, it is somewhat averaged over the whole sample, but yes, those are schematic and meant to be instructive rather than exact.
Mm-hmm.
Next question here. Yes?
Question. If I heard you right, you said that at least 2 of the IAU299 planets, I think C and D, or D at least, had rather T-dwarf-like specular appearance in those spectra that you showed. I mean, quite amazing spectra, but the signal-to-noise also seems rather low. But the specular energy distribution didn't look at all like a T-dwarf because there's practically no flux in the J-band. So how do you reconcile that, or what is the T-dwarf type like feature in those spectra?
I think just the general shape. I mean, it doesn't show, it's not an object that shows a lot of methane absorption, but they fit it to a T2 template, which is not too far into the T-dwarf. So I think it's a little tricky to say, given that they are very low resolution spectra. And I think it would be very interesting to see what they look at higher resolution. I suspect a different spectral template might work if you looked at higher resolution.
More questions? Yes, in the back. Just wait for the mic.
Hi, if I get it right, you seem to be talking about the detection of carbon monoxide in the atmosphere of giant planets. I wonder what is your comment about the detection of carbon monoxide in the atmosphere of, say, Earth-like exoplanet? Is that possible? And how far away from that? Thank you.
Yeah, good question. So, I mean, the thing, I feel that the likely first detections, direct imaging detections of Earth-like exoplanets will be with these ELTs. So the question is, are they just going to be so faint that we're trying to get only a detection, or can we get a low-resolution SED? My guess is probably that it is just going to be a detection with ELTs, and that we're going to have to wait for space-based platforms to really get that spectrum and see if we can find carbon or oxygen in these atmospheres.
We still have some time for questions. Here.
Question in the comments. The question is that when you were describing the important components to be able to directly image planets, one of the things you didn't mention was the enormous work that's been put into processing the images.
Yeah.
With the powerful algorithms like Loki, things that Christian Marois has been had a deep impact in to develop. And even with like the newest generation of that, with adaptive Loki or with SOSA, you get gigantic swings in signal to noise. So I was wondering, with your survey, if you see any dependence on how deep of contrast you get, depending on exactly how you process the data. And the comment is, I think you should interpret the spectrum of the IAU299 planets with extreme caution, because the photometric points between B, C, D are almost identical from work that I've done.
All right. So, detection algorithms. They do play a huge role. It's clear that in some cases that Loki or T-Loki really do help you go a lot deeper. One thing we found, at least for the data from the Nikki campaign taken in dual band imaging, is that we actually didn't see a lot of improvement from Loki, which is interpreted mostly as due to the dual band subtraction. But I would agree that those are very important. It's important to apply those algorithms to try to get the best contrast possible.
Okay, one last question. Okay, otherwise let's thank Beth again for a very